So it looks like a big class again. Am I loud enough? Okay, this is engineering math 2. So if you happen to be in the wrong place, then maybe the best time to change your mind. Okay. Usually I start with the grade policy that which most of you will be very interested in, right? Grade policy. 학점 어떻게 주는지. So we are going to have about 3 quiz. Normally 1 hour quiz. Sometimes 2 hours. So plus alpha. So usually we have 3 quiz and 1 final. And 60%, 40%. And usually less than 10%. A plus. So other than that, I'm usually quite generous for the grade. So about maybe 2/3 got B plus at least. And it is very difficult to get an F either. So you have to be eligible for F. You have to be absolute to 0. So if you got maybe 10 points out of 1,000, you will still get T minus. And no homework. I usually give a lot of homework, but you don't have to turn in. It's just for your work at home. And I and my TA doesn't have enough time to grade every homework because in the past, I realized that about 20% of you do the homework and the other 80 just copies it, right? So it doesn't really make any sense to check all the homework. But nevertheless, I will give you homework, and better do it at home. So any questions about the grade policy? How is my English? Is it understandable? Am I talking too fast or too slow? It's okay? All right. And for each quiz and final, you are allowed to prepare a cheating sheet. It depends on the amount of the hours that are allocated to each quiz or final. So normally A4 size, one-sided, then you can write down everything you can. So you can bring the cheating sheet for your quiz or final. The reason I'm allowing to prepare cheating sheet is I found that it's the only time you study too, right? The cheating sheet is in Korean, it's cunning paper. And I found that for most of the students, the only time they study is for preparing for cunning paper, right? So that's from my experience. And we are going to start with a complex variable for this semester. Topic number 1 is complex variables. Some of you might have taken or learned about complex numbers in high school. 복소수? So how many of you are familiar with the complex numbers? Raise your hand. Or at least heard about it or have seen that. 복소수 배운 사람? So about a few students, right? So complex number is based on imaginary numbers. I think you are familiar with the number systems. You have learned natural numbers. One, two, three, four, 5, right? So you probably learned natural numbers when you were the first grade, or maybe in kindergarten. 자연수. Natural number is called 자연수. So natural number, you can add them together, right? So let's say natural number is a set. It's 1 plus 2 is 3. It belongs to natural number, right? How about multiplication? 2 times 3 is 6. It belongs to natural number, right? How about subtraction? If you subtract 2 from 3 from 2, what do you get? Which is minus 1. It doesn't belong to natural number, right? So it doesn't belong to natural number. How about division? 2 divided by 3. It doesn't belong to natural numbers. For multiplication, we use base 10. Base 10 is 10법. So we say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you change it to 11, right? The reason why you are using base 10 is we have 10 fingers. So how long have we been using base 10 number systems? How long? What do you think? How long do you think we have been using these base number systems? Probably 100,000 years. So the origin, long time ago, there was a caveman with hunting rabbits. And also there was the group of people living near the seashore called fishermen. They hunt fish, right? So fisherman was get bored of eating rabbit all the time, and same as the fisherman was bored, or they didn't like eating fish all the time. So once upon a time, they met in between and decided to exchange one rabbit for one fish. So how do they do that? They use the fingers, right? One rabbit for one fish. So if it is less than 5, then you can just use one finger each, right? Okay, if it is more than 5, what do? Use your 2 hands, right? So one finger for one fish and one finger for one rabbit. And, what happens if there is more than 10 rabbit or 10 fish? What do? Very simple. Any suggestions? If you have more than 10 rabbits to exchange with the fish for each one, what do? Bring your friends, right? One more people, you can count up to 20, right? So if you have more rabbits, like 23, what do? Bring more people, right? So at least one finger for one rabbit, one items each other, right? That's the origin of the base 10 systems we have been using for 100,000 years. Okay, somebody might ask, what happens if someone has 6 fingers? It happens, right? Maybe 0.1%, but that's very rare. So you can just ignore. So we can ask another question. What happens if 65 million years ago, big meteorite didn't hit Earth? And if somehow the dinosaurs survived and they become intelligent and they are teaching math, what kind of number system are they going to use? How many fingers does dinosaur have 3. So if somehow, instead of me, some dinosaur is teaching, and dinosaur is listening, they will use base 6 system, right? So in a way, that the reason why we are using the base 10 system is probably the result of the evolution for our species. And because the bad luck for the dinosaur. If somehow the meteorite didn't hit Earth, and if they survived, and they evolved, then probably our ancestors didn't have a chance to become intelligent, and then probably dinosaurs still rule the Earth. And in that case, I think they are going to use base 6 system, right? This is for the fun. I mean, next number system you learn probably. You have to wait until middle school for integer. It's called z. It's 1, 2, 3, and you have 0, and you have -1, -2, etc., etc. So integer system is natural number system with 0 plus minus of natural numbers. And you can add them together. 1 minus plus -3 -2 belongs to integer, right? Likewise, subtract. You can subtract -1, -2. Again, belong to integer. You can multiply -1 times 3 is -3, belongs to integer. 2 divided by 3, nevertheless, still doesn't belong to integer. So the first system, number system, that is close to the 4 arithmetic operations. This is called the 4 arithmetic operations. 4 arithmetic operations. 출석부 있나? 출석부. Addition, subtraction, multiplication, and division. So addition is 더하기, subtraction is 빼기, multiplication is 곱하기, and division is 나누기. So those are the 4 basic operations in mathematics. It's called arithmetic operations. And it is very important that the number system you are going to use is close to the 4 arithmetic operations, because if you like to expand some functions, if fx1 plus x minus x squared plus 2 of x cubed. Assuming that this is your expression for functions, and this is your addition operation, right? This is subtraction. This is you multiply x by x, multiplication. This is division, right? So any simple function representation can be represented by 4 basic different arithmetic operations. So if you like to express your number system using computer or some operations using computer, then the given number system has to be close to the 4 basic arithmetic operations. And so far, natural numbers and integers are not close to the 4 basic arithmetic operations. The first number system that is close to the 4 basic arithmetic operation is called rational numbers. This is ratio plus adjective. To make the ratio. Ratio is a ratio, right? A over B. So any number system Q is given by N over M. And M belongs to integers. So rational number system is the first number system that is close to the 4 basic arithmetic operations, and was known to humans since 10th century BC. People present. So 10th century BC belongs to like a Chu dynasty in China, and probably early Greek or Trojan civilization. The reason why our ancestors invented rational numbers, they need to have some particular number system that is close to the 4 basic arithmetic operations, especially the division. Why? To tax people. So they need to find the area for the farming land size. So you need to be able to divide. The 10th century BC is about the time in history that the kingdoms was established. So until 2 or 3 century BC, they believed that they have a perfect system called rational numbers. But somebody asked the following question: is there a number called if 2? So some mathematician asked the following question: is there any rational numbers that gives number 2 when squared? And the mathematicians at the time tried to show that it is possible to find a number that is rational numbers, but not, right? Do you know who is the mathematician who asked the following question? Pythagoras. We say Pythagoras. The Pythagoras didn't believe that the rational number system is perfect. So he tried to challenge the established mathematicians at the time that if there is any number system that gives the following answer. And we now know that there is a number that, right? So x is square root of 2. It's called irrational number. And rational number together with irrational numbers forms a real number system. Called R. So from the practical point of view, the real number system is probably sufficient for many engineering problems and many scientific problems, right? Wow. We have 115 students. Wow. We have 2 foreign exchange students in my class. Let me see. Mr. Lawrence, attending the class? Nope. Mr. Muhammad Chan? Nope. Okay. One more policy for grade. Usually I don't check the attendance. So, I mean, you don't have to bother to be in my class. But once in a while, I do have a quiz not announced. Just check the attendance, maybe once or twice a semester. So if you happen to be in the class, then you are safe. Otherwise, it's okay. Because the surprise quiz you should count about maybe 10 points out of 1,000. So 10 points is not much, right? But if you happen to be in the borderline between like A to B plus, if your score is just at the borderline, then 10 points can change your grade. But it's up to you. We don't force you to attend the class. And when we have a surprise quiz, usually we lock the door. About 16th century, unfortunately, the record didn't survive. Who asked the question that someone asked the question that x squared gives -1. It can be a stupid question, but nevertheless, as a mathematician, you have a freedom to ask any questions, right? So, but history doesn't record who asked the question, but someone about 500 years ago asked the question, if there's any number that squares becomes -1. And he invented the following convention, I equal to square root of -1. And he named it imaginary number. Well, I think that is reasonable because this number actually doesn't exist, right? It only exists in your imagination. So whatever the mathematician, he named the number as imaginary number, and then we decide to build a number system based on that. So say z x plus I y, and x and y belongs to real number, and this new number is called complex number system. So it may be interesting to check whether that the complex numbers, you can define like 4 arithmetic operations, and if the resulting the calculation is within the number system. Let's say I times I is -1. So this is our assumption or premises. And we can add them together, z1 plus z2. x1 plus iy1, x2 plus iy2, x1 plus x2 plus iy1 plus iy2, and we can combine them together, iy1 plus y2, and since x1, x2 belongs to real number, y1 plus y2 belongs to real number, right? So this number system is actually belongs to complex. So we found that we can define the addition, and they are close to the addition. The result is also belongs to complex numbers. Probably I should wear a mask or not. I mean, it turns out that COVID-19 is still rising again. So I always bring this, especially when I take the subway, but hope it's okay. How about subtraction? C1 minus C2, x plus I y1 minus x2 plus iy2 is x1 minus x2, y1 minus y2. So it turns out that x1 minus x2 also belongs to real number, right? And y1 minus y2 also belongs to real number. So it has to be within complex numbers. So we can say that for two complex numbers, we can define subtraction. And the result is, again, the complex numbers, right? Multiplication, C1, C2. x1 plus iy1, x2 plus iy2, x1, x2 plus I, y1, x2 plus I, x1, y2 plus iy1, iy2, x1, x2 plus I, x1, y2 plus y1, x2 plus y1, y2, I 곱하기 I cross I, which is minus 1, right? So this is x1, x2 minus y1, y2 plus I, x1, y2 plus y1, x2. So this belongs to real number. This belongs to real number. So as a result, it belongs to not real but complex, right? So we found that you can define the multiplication for two complex numbers, and the resulting operation gives also complex numbers. So at least the complex number system is close to addition, multiplication, and subtraction. What about the division? C2, C1, x2 plus iy2, x1 plus iy1. So how do we represent this in terms of a known system, real plus imaginary part of the real system, right? So I will give you one very simple rule. Okay, I can put my name. Do nothing. When you have a complex problem, do nothing. So do nothing actually means add 0 or by 1. When you encounter complex problems, complicated problem. So there are many cases that you face a very difficult or complicated problem. And my advice is do nothing. So do nothing in mathematics is you add 0. It doesn't change, right? Or you can multiply by 1. It doesn't change either, right? So let's try to apply this wisdom. Then in this case, what kind of do nothingness we can do? Multiply by 1. So how do you multiply by 1? You multiply by something and divide by the same thing. The same as 1, right? So I'm going to use the do nothingness. x2 minus iy2, x2 minus iy2. So overall, this is 1, right? Whatever the expression is, we multiply by something, and you divide by the same thing. It doesn't change anything, right? It's same as just do nothing. However, x2 plus iy2 times x2 minus iy2. Probably you have seen this number system. You just change the sign of an imaginary number. This has a name. Complex conjugate of x2 plus iy2. So complex conjugate, probably you learned that by the name of 혈례복소수 or 공액복소수? Which one? 혈례복소수, right? So when I was in high school, it was called 공액복소수. It was 1978. Probably most of you was not born, right? Yeah. So x2 plus iy2 times x2 minus iy2 is x2 times x2 plus iy2 times x2 minus ix2 times y2 plus iy2 minus iy2. So these two cancel each other, and it becomes x2 squared plus y2 squared. So z2 over z1, which is x1 plus iy1, x2 plus iy2 is x2 plus iy2, x2 minus iy2, x1 plus iy1, x2 minus iy2, x2 squared plus y2 squared, x1, x2 plus y1, y2 plus I, x1 minus y2 plus x2, y1. So it turns out that x2 square plus y2 square, x1, x2 plus y1, y2 belongs to real number, right? And x2 square plus y2 square, x2 y1 minus x1 y2 belongs to R. So therefore, z1 over z2 belongs to complex number. So we just checked that this complex number system is close to 2 for basic arithmetic operations, and therefore you can define any functions. Probably let's take a break for 10 minutes, and even though I don't check, we found that the complex numbers satisfies for basic arithmetic operations, right? So you can define complex numbers. How can we define the numbers, complex number system, complex functions? So since z is actually x plus iy defined, also you can represent that in terms of a two-dimensional Cartesian coordinate in the point as a z. So complex number system can be also defined as a point in two-dimensional Cartesian plane. So z can be defined as a point in two-dimensional plane in Cartesian coordinate. So Cartesian coordinate is actually named after French mathematician Descartes. So if this is r and this is theta, then x can be defined as r cosine theta, y is r sine theta, and r is simply square root of x squared plus y squared. Theta is arctangent y over x. So assuming that we have 2 points, z1, z2 is x1, y1, x2, y2, or r1, theta 1, theta 2, r2. So z2 is r1 cosine theta 1 plus I sine theta 1, C1. C2 is R2 cosine theta 2 plus I sine theta 2. And we call this representation as a polar representation. 극좌표 표현, something like that. So if we multiply by 2 complex numbers in polar coordinate, then z1, z2 can be represented as r1 cosine theta 1 plus I sine theta 1 times r2 cosine theta 1 plus I sine theta 2, which is r1, r2 cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2 plus I R1, R2, cosine theta 1, sine theta 2 plus cosine theta 2, sine theta 1. Somehow this expression might be familiar to you since high school days, right? 삼각함수의 가법 정리, addition theorem. Are you familiar? Or anybody still remember that? Okay, so what is that? Can you, Mr. Cosine theta 1 plus theta 2 is? Okay, cosasa. Cosine theta 1, cosine theta 2 minus sine theta 1, sine theta. How about sine theta 1 plus theta 2? Sa cosa. Right? Actually, I memorized that way. So you probably have memorized the addition theorem for the complex numbers, but probably toward the end of, I don't know, maybe next week, we are going to actually prove that using complex numbers. So this turns out to be R1, R2, cosine theta 1 plus theta 2, I sine theta 1 plus theta 2. So we can multiply 3 complex numbers, 4, etc., etc., right? So let's consider a very simple case when R is equal to 1. Special case. R is equal to 1. Then Z is x plus IY is represented by cosine theta, I sine theta, right? How about G squared? Cosine 2 theta plus I sine 2 theta, right? And you can continue, Z to the n is called cosine n theta plus I sine n theta. Let's say this is something f of theta. Then we have the following relation. F of theta times the power of n is same as f of n theta. If you have a power of n, it's same as the function with the n times of argument, which is that kind of function. Any guess? Anybody can guess what kind of function it is? Is it? Maybe exponential function. Alpha theta. Then exponential alpha theta to the n is exponential alpha n theta, right? Which is actually f n theta. This is f to the theta to the n, right? So this is exponential function. So alpha is, so f theta exponential alpha theta cosine theta plus I sine theta. So let's use Taylor expansion. You probably learned in your freshman calculus 미적분. So exponential alpha theta is 1 plus alpha theta plus 2 factorial alpha square theta square 3 factorial alpha cube theta cube. Cosine theta 1 minus theta square over 2 factorial 4 factorial alpha 4. Sine theta theta minus theta cube over 3 factorial. So 1 plus alpha theta plus 2 factorial over alpha square theta square plus 3 factorial alpha cube theta cube, same as 1 plus 1 minus theta square over e factorial plus I theta minus 3 factorial theta cube. So that's obvious. Alpha is I, right? You can see that alpha is I. So we just obtained probably the most important formula in mathematics, called Euler's formula. Thus we obtained I theta is cosine theta plus I sine theta. It has a name called Euler's formula. Let me Google it. Euler is a Swiss mathematician in 17th century, 18th century, I think. Euler. I used to remember a lot, but not anymore. Maybe I'm getting old. Leonhard Euler. He 1707 to 1883. He was born in 83. It's a Swiss mathematician, 1803. So in Korean, I think it's about Yeongjo to Jeongjo time, Yeongjeongjo 시대. So Euler is a mathematician in Yeongjeongjo 시대. So let's try to exploit the basic properties of the trigonometric functions defined in complex numbers. So exponential I theta cosine theta plus I sine theta, according to Euler's formula. How about minus I theta? Cosine minus theta plus I sine minus theta. So that is cosine theta minus I sine theta. Number 1, number 2. So if we add 1 plus 2, what do you get? Exponential I theta plus exponential minus I theta is 2 cosine theta. So cosine theta is defined as exponential I theta plus exponential minus I theta divided by 2. 1 minus 2. exponential I theta minus exponential minus I theta is 2I sine theta, right? So sine theta 2I over exponential I theta minus exponential minus I theta over 2I. So once we define exponential function, then we can define the corresponding trigonometric functions. So cosine theta is defined as exponential I theta plus exponential minus I theta. Sine theta is exponential I theta minus. If theta is defined the following way, if theta is defined by I times some number zeta, then you can still apply the same definition. Then cosine I zeta is exponential I zeta I zeta. Exponential minus zeta plus exponential zeta. That is cosine hyperbolic zeta, right? So cosine in complex numbers, cosine and cosine hyperbolic functions are related to each other. So cosine I zeta is cosine hyperbolic zeta. How about sine? Am I going too fast? It's still okay? All right. Sine I theta 2I exponential I theta minus exponential I minus theta is 2I exponential minus theta minus exponential zeta. So this becomes I over minus 1 times 2 times exponential zeta minus zeta. I times minus 1 times sine hyperbolic zeta, right? And we can apply the principle of doing nothing, right? So I would apply I, right? So it becomes minus 1 minus I sine hyperbolic zeta. So this is I sine hyperbolic zeta. So we have the following relationship. Cosine I zeta is cosine hyperbolic zeta. Sine I zeta I sine hyperbolic zeta. So now we are ready to define cosine z. The definition of complex trigonometric cosine z, which is cosine x plus iy, right? So which is defined by the following way: 2 over exponential iz minus iz, right? Using Euler's formula. So this is exponential I x plus iy minus I x plus iy over exponential ix minus y exponential minus ix plus y. So this is exponential y 2 over exponential minus ix exponential minus y 2 over exponential ix. Copy. Okay, so we don't need 2 here. We have 2 here. So that is 2 over exponential y cosine x minus I sine x exponential minus y over 2 cosine x plus I sine x, right? So we can factor with the cosine x. We have exponential y plus exponential minus y minus I sine x 2 over exponential y minus exponential minus y. So this is cosine x cosine hyperbolic y minus I sine x sine hyperbolic y. On the other hand, cosine x plus iy. If we use addition theorem, what do we get? Cosine x cosine iy, right? Minus sine x sine iy. So which is same as cosine x cosine hyperbolic y minus I sine x sine hyperbolic y, right? So they are the same expression. This expression and this expression are the same. So we just established the addition theorem in the complex domain. So we have the following addition theorem. Is valid in complex domain. addition theorem, 가법 정리, is valid in complex domain too. So using this, we can easily define sine, right? So from now on, you are just going to use the addition theorem. Will be just enough, right? Because we have already seen that for cosine z, the component by component expansion gives the same result for the addition theorem, right? So you can use this approach. Just use addition theorem for defining complex numbers from now on. Just let you copy if I'm going too fast. Maybe. How about sine z? Sine z. Sine x plus iy. Sine x cosine iy. Cosine x sine iy, right? So sine x cosine hyperbolic y plus I cosine x sine hyperbolic y. So how about tangent? Tangent can be a bit complicated, right? Tangent z is sine z, cosine z over sine z. So sine x I cosine x sine hyperbolic y, cosine x cosine hyperbolic y minus sine x sine hyperbolic y. So somehow we have to reformulate this because you don't want to have an expression still I in the denominator. Okay, for this is called denominator. This is called denominator. In Korean, denominator is 분자, and denominator is in Korean called 분모. So we like to normalize or rationalize the denominator. We would like to rationalize the denominator or make it real. So what do? Same approach, do nothing, right? Just multiply the same complex conjugate of denominator in both numerator and denominator. So tangent z, let's do that. I think it may take about 10 minutes to do all the math, but I'm just going to show that for tangent z and probably give you as a homework for the other, like a cotangent z, sinc z, cosecant z. So we have to breathe deeply before we move on to the next page. All right. 이거 바꿔야 되겠다, 그렇지? 코탄젠트 이렇게 바꾸면 되겠지?
공지하겠습니다.
그러면 so tangent z sine x cosine hyperbolic y I cosine x sine hyperbolic y cosine x cosine hyperbolic y minus I sine x sine hyperbolic y. And we know if we multiply the complex conjugate together, I. Denominator is easy, right? We already know the answer. The square of the real part plus square of the imaginary part. So sine square x cosine square y plus cosine square x sine hyperbolic square y. On the other hand, cosine x cosine hyperbolic y sine x cosine hyperbolic y minus sine x cosine x sine hyperbolic square y plus I. Is it I sine square x square y plus cosine square y square y. Maybe you can have minus sign, which is convenient. So sine x square sine hyperbolic y cosine hyperbolic y plus cosine square x cosine hyperbolic y sine hyperbolic square y. So how do we simplify this expression? Cosine square x sine hyperbolic square y. The first denominator of the real part is sine x cosine x. And we have cosine hyperbolic square y minus, right? And minus I sine square x cosine hyperbolic square y plus cosine x sine hyperbolic square y. And we can have sine square x plus cosine square x times sine square y cosine square y, right? What is this? Cosine hyperbolic square y minus sine hyperbolic square y. You should be able to remember that it's 1. How about this? Sine x square x plus cosine x square 1. Another 1. So it turns out that we have a very simple expression. That is let me just copy this sine. Sine x cosine x minus I xx 를 정의했네. 정에서도 코탄젠트. 내가 탄젠트라고 했는데 over paste. So this will be the common denominator. Very nice, right? We have hyperbolic y. Is there any way that we can simplify the denominator? Let's try to see that. Sine square x cosine hyperbolic square y plus cosine x can be put into minus sine square x sine square y. So that is, we can put together sine square x cosine hyperbolic square y minus sine square. This is sine. Sine square y plus sine square y, and this is 1, right? So we have sine square x plus sine square y. So tangent to z can be written as sine square x sine hyperbolic square y sine x cosine x minus I sine hyperbolic y cosine hyperbolic y. So this is his expression for tangent z. So let me ask ChatGPT whether this form is correct. Tangent z. So ChatGPT doesn't normalize the denominator. So maybe you have to trust me, or maybe just Google. Let me just check the expression is correct. Tangent C. Okay. Sine, cosine, sine, correct. So my result agrees with Google's result. So maybe just one more. 탄젠트가 아니라 코탄젠트. 여기도 그거 학생 고마워요. 내가 실수했는데. sequent cosine z, maybe simpler than the other one. This is cosine x cosine hyperbolic y minus I sine x hyperbolic y, right? So cosine square x cosine hyperbolic square y plus sine x sine hyperbolic square y cosine x cosine hyperbolic y plus I sine x sine hyperbolic y. And probably normalized by using 1 minus cosine square x. Then again the same expression, sine square x plus sine hyperbolic square y, right? Same with the cosine x cosine hyperbolic y I sine x sine hyperbolic y.
그리고 질문 하나.
네. So probably I just give two homework. See, which is easy. Cotangent C, which is a bit harder. As I told you in the beginning, the homework is for your own benefit. So just do at home and just don't bother to give it to me. So I think two homeworks will just take you about half an hour, right? And best time to do the homework is, do you know when? How many of you have taken my class in the spring semester? So I gave you the best time to do your homework, right? To do up in the blind date. So you are waiting at the coffee shop. You have your homework. And your date doesn't show up. In Korean, it's called 바람 맞았다, 그죠? So you still have done your homework, right? So even though you stood up at the date, you still have finished your homework. So that's good for you anyway. So best time to doing homework. To do the homework. 2. So we have studied the trigonometric functions first using Euler's formula, but the most useful function is polynomials, right? So 그럼 호목은 탄젠트겠지, 그지? z is x plus iy. Z square is z times z. X plus iy, x plus iy, x square minus y square plus I2xy. Z to the cube, z squared times z, so which is x squared minus y squared plus I2xy, x plus iy is x cubed xy squared plus I2x squared y, ix squared y minus iy cubed minus 2xy squared. So that gives x squared, x cubed minus, let me see, x cubed, xy squared, 2x squared, xy squared minus 2xy squared plus I 2x squared y plus x squared y minus y cubed, x cubed minus 3xy squared plus I 3x squared y minus y cubed. Okay. So maybe I'll give you another homework. X4, not X4. Z4, Z5, Z to the 6 as homework. I think they will take about another half an hour. So for this homework, I think for this week, maybe 1 hour will be enough. So 2 trigonometric functions and 3 polynomial functions. And probably we can stop here today and then continue next week. What do you think? And I will put my class on YouTube. So my YouTube address is Professor David An. You can check for this. So if you have time, maybe you can check 좋아요. All right. So any questions? 보면은 뭔지 모르지만은 이게 F의 n승이 되는 거예요. F의 n승이 F의 반해가 n승이 됩니다. 이 두 개를 만들, 이 조건 만든 함수가 뭐가 있을까? 보니까 지수함수. 네. 이런 성질을 맞출 때 지수함수가 있습니다. X함수로 같은 걸 해보자 했더니 알파가 아니더라. 아이씨. 네. 예.
아,
글쎄. 네.
요거를 지금 관계하는 이게 세트.
똑같이 봐요. 두 번째 타면은 코사인 시타 제곱 빼기
제곱하면 이렇게.
그러니까 F의 시타의 n승이 F의 n 시타가 되는
그냥
수가
그대로 써도 n배하면
X함수 쓰니까 그 합법 정리가 무수 수에 대해서 있으니까
탄젠트 사인분의 사인이랑
코탄젠트 코사인 아니면 코사인 이게 잘못했네. 코탄젠트를 바꾸자.
이거 탄젠트가 아니라
코탄젠트
근데 왜 하필 탄젠트도 아니고 하필 탄젠트?
내가 실수 안 했지.
아 그럼 요거 뒤집어요.
아니 이게 코탄젠트 전에
그냥 코탄젠트로 정해. 아
응. 그러면 내가 틀렸으니까 이게 몇 페이지에 있었지?